Okay, welcome back. Let's see if we can't knock out this chapter 8 stuff. So, we're talking about periodic trends here in the periodic table. We're talking about atomic radius. It's kind of a tricky idea, this atomic radius. The idea of what's the distance from the nucleus to the edge of an electron cloud? You might think to yourself, well, geez, we just talked in class about Heisenberg uncertainty. We can't know the exact position and momentum of an electron, so if you can't know the exact position of an electron, then how are you supposed to get the distance of an electron cloud for some subatomic particle wave doohickey? Well, that's a good question. The answer is we take something called a covalent radius, which means if we can get a covalent bond between, let's say hydrogen and hydrogen, you're right. We don't really know where the end of that electron cloud is, but we do know where that super dense nucleus is and where that super dense nucleus is. So if we can get that distance in picometers or angstroms between one dense nucleus and one dense nucleus and divide it by 2, then between friends we can say this is probably the radius of that electron cloud. So that's how we find atomic radius. Now let's look at how atomic radius changes. If you look at your periodic table, which again will be very useful, if you go down a group or a family, your atomic radius gets a lot bigger, which makes sense. You add electrons, you add electrons, you add electrons, you add electrons, your electron cloud gets bigger. No duh. Well, if you look at this one, it gets a little weirder. You go across a period, you add electrons, it gets smaller. You add electrons, it gets smaller. You add electrons, you add electrons, you add electrons, you add electrons, and your electron cloud's not growing, it's shrinking. So it's kind of an odd thing, but let me explain it to you. Here, we talked about effective nuclear charge and this idea of the nucleus pulling on electrons. We've talked a little bit about electron affinity, electronegativity here in just a minute. As you add electrons, lithium, beryllium, boron, go ahead and look on your periodic table and find out what period they're in. I'm seeing it's the second period, third period. You move across the period here. We add electrons, but they're still in the principal energy level of 2. We add electrons, they're still in 2. You add electrons, they're still in 2. Add electrons, n still equals 2, n still equals 2, n still equals 2. It's sort of like adding more and more negatively charged magnets and more positively charged magnets, because we're adding protons as well, but not giving them any more space. And so if you shove a whole bunch of positive and negative magnets into a little teeny tiny circle on the desk, and you add more and more positive and negative magnets in the same size circle on the desk, they're all going to get stuck together. They're going to be drawn in kind of close, right? That's what's going on here. Now as you look over here, lithium, sodium, potassium, they're growing. They're growing as you move down. And this, we add protons, we add electrons, like we did before. But as we move down, now we're in the n equals 3 principal energy level. So we just created a whole bunch more space. Add protons, add electrons, create a whole bunch more space. N equals 4, n equals 5, n equals 6. So we're still adding protons and electrons, but we're giving them more space to be in. Here we're adding more protons and electrons, and we're not giving them more space. So it's going to suck that electron cloud in tighter and tighter and tighter as you move across a period. So here you look at atomic radius. Lithium going to fluorine, we've got atomic radius in picometers in our atomic number. Lithium to fluorine, it's going to get smaller and smaller and smaller as you move across. Sodium to chlorine, smaller and smaller and smaller as you move across. Now we said we're talking about trends here. So you see that it's not always perfect. Here we kind of make this little dip up where the atomic radius gets larger. Then it gets smaller. Here we make a big dip up where atomic radius gets bigger, 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 smaller, smaller, smaller. But for all of these, if you were graphing them on something neat like, Excel or Veneer, or whatever you were using to make your graph, if you were to, highlight this and say, draw me a best fit line your best fit line is going to be like sloping down, sloping down, sloping down, sloping down. So the trend is that it's decreasing. So just so we kind of understand that. Now here's kind of a cool chart. Comparing your atomic radius, so a lithium atom and a sodium atom, with your ionic radius, so a lithium cation and a sodium cation. And what we find is this. When the lithium forms the cation, it gets smaller. Why would it get smaller? Let's think about it. What's it doing to become Li+? It's losing an electron. So if you lose an electron, is your electron cloud going to get bigger or smaller? Probably smaller. And here, sodium loses an electron. The electron cloud gets smaller. Potassium, it's all the same. Rubidium, cesium, it's all the same. Then we look over here, and we look at a different set. Fluorine, chlorine, bromine, and iodine are halogens. Fluorine gains an electron to become the fluoride ion, and it gets a larger atomic radius. Shouldn't say that. A larger ionic radius, because if you gain an electron, your electron cloud gets bigger. Chlorine does the same thing. Bromine does the same thing. And so it kind of looks like this. Lithium wants to bond with fluorine. So to do that, lithium has to give up an electron. Lithium becomes smaller. Fluorine gained that electron. So fluorine becomes bigger. Now as a result, lithium's more stable, fluorine's more stable. So it's a good change. But to get there, their electron cloud size is going to change pretty dramatically. So a cation, positively charged, is always smaller than the atom that it's formed from, and vice versa. An anion is always larger than the atom from which it's formed. So here's the radius in picometers of a few familiar elements, and it just kind of gives you your numbers. 171 picometers, 140 picometers. Not something you need to commit to memory. So here's kind of a neat application of this. Francium, kind of a weird little element. Not something we get to spend a lot of time with because it's radioactive and it decays kind of quick. It actually decays really quick. T1/2 is half-time, or a half-life rather. Half-time. Funny. This isn't sports we're talking. Half-life. Sorry about that. So out of all the elements we know, only 2 elements are liquids at room temp, lab temperature. Bromine's a liquid, mercury is a liquid, and our knowledge, that's it. Now francium has such a short half-life, 21 minutes, half the sample's gone. 21 more minutes, half of what was remaining was gone. And so the stuff that we're finding is in such teeny tiny amounts, we don't have a whole lot of chance to experiment with it. But what we can do is we can look at our periodic table and say, okay, where's francium? So take a minute and find francium. Once you've found it, you can look at the other elements that are in the same family. We got lithium. We got a lot of lithium. We can do experiments with that. We got sodium. We got potassium. We got rubidium. We got cesium. We have these. They hang out with us. This is nice. So we can do experiments with these. And what we can find is where they melt at. So lithium melts at 180 and sodium melts at about 100. Potassium melts at this temperature and rubidium at 30, 40. Cesium about that 30 mark. And we can draw a graph. And we can say, okay, if we could get francium 223 isotope at room temperature, its melting point based on periodic trends, because that's the point of having a periodic table, so look at periodic trends, would be right about that 25, 26 or so degrees Celsius. So if we had francium sample in a warm lab, it could very well be a liquid. I don't know if it is. We don't know if it is. We don't have it in testable amounts really, but there's a pretty good chance it would be liquid. So just kind of something to think about. Kind of cool. So let's talk ionization energy. We just talked cations and anions, so why not? Ionization energy is the energy required to remove an electron from a gaseous atom in its ground state. So to simplify it, how much energy does it take to pull an electron away? The answer is depends on the atom. So here you've got your atom, or rather your ionization energy plus whatever atom you're dealing with goes to that atom becoming cation plus 1 and the electron that you pulled away. That's called our first ionization energy. How much energy did it take the first electron away? Now if we're going to do it again, we have to do a different energy. And we're going to take that product, that cation, and we're going to try to pull another electron away to make it a 2 plus. Some elements are okay with this, and some elements are really not okay with this. We get that other electron away, that's a second ionization energy. That's going to be pretty tough to do. Try for a third. So let's take that product. We got 2 plus cation. Let's see if we can pull another electron from it, make it a 3 plus and a free electron. That would be our third ionization energy. And at this point, the energy that we're using is really going to be a lot. So your first ionization energy is always less than your second ionization energy, which is always less than your third ionization energy. So here's some elements you can kind of look at. Bear in mind, this is kilojoules per mole. This is a lot of energy we're talking about here. If you want to take an electron from a metal like potassium or calcium, they are kind of electron givers anyway, so they're cool with it. 400 kilojoules, sure, have the electron. 500 kilojoules, sure, have the electron. Lithium, metal, 500 kilojoules, sure, have the electron. But as you go up, you want to take a second electron? I don't know, let's look at lithium on a periodic table. Where's lithium? Lithium's 1s1. It's an alkali metal, so you want to have the first electron? Sure, by all means, take it. I'll be more stable. You want to have the second electron? Not really, because that would take lithium from being like helium to being like hydrogen from an electron configuration. Not very stable at all. So that's going to take a ton of energy to make him that unstable. And if you want the third electron, that's all he has left. There's no way he's going to give that thing up. That's crazy. 11,000 kilojoules? Holy smokes. So you kind of get the idea. Now let's look at some stuff that's not metals. Let's go down here. How about fluorine? Now he's a non-metal, and he's not an electron giver. He's an electron taker. And so to want to take the electrons from the electron taker, we said he's kind of a big greedy guy. He likes to steal electrons. He's not an electron giver. So how much energy does it take to take one electron away? A lot. We're already at 1,000. Second electron, even more. Third electron, even more. Fourth electron, forget about it. This is a ton of energy we're talking here. Neon, noble gas. You want to give up an electron? Nope. I'm a noble gas. I don't want to do anything with my electrons. Leave me alone, right? We start at 2,000 kilojoules. And so kind of gives you an idea when you look at these at elements that want to give electrons up to be more stable and elements that really, really don't want to give electrons up. And so here's your trend. Kind of what we talked about before, just in a graph. Hydrogen, sure, it'll give an electron. Noble gas, not a chance. Metals, sure. Noble gas, not a chance. Metals, sure. Noble gases, not a chance. Metals, sure. You get the idea. All right, filled shell, filled shell, filled shell. You guys know noble gases have filled shells, right? Cool. All right, so general trends in the first ionization energies. You're going to increase that energy as you go up. You're going to increase that energy as you go over. So electron affinity is kind of like electronegativity, not really the same. Electron affinity is negative of the energy change that occurs when an electron is accepted by an atom in a gaseous state to form an anion. So here we say if we've got a gaseous atom, it's accepting an electron to become negative. How much energy does it give off? So for fluorine plus an electron to become F minus, that's good. He wants to do that to be more stable. So he can give off a little bit of heat, negative 328 kilojoules. And so what's the electron affinity? So his affinity for that electron is positive 328 kilojoules per mole. If you have a high affinity for something, it means you want something or you like that something. Fluorine has a high electron affinity. Fluorine really likes electrons. Oxygen does too. Oxygen really likes electrons. It'd love to be O2 minus if it could. Negative 141 kilojoules, so its electron affinity is a positive. 141 kilojoules per mole. And so here's kind of a graph of some electron affinities. Lithium and beryllium, relatively small electron affinities. Do they really want to get other electrons? And they're metals. Not really. 50, 60, 40, 2. Not really. You go over to your nonmetals, your electron takers. What's their energies look like? Pretty high. 100, 200, 300, 300, 300. They really like electrons over here, for sure. Transition metals, a little bit of weirdness. Not really so much here in this kind of metalloid area. They're sort of middle ground there. So here's your atomic number again. Electron affinity. How much do you want electrons? Metals, not so much. Halogens, absolutely. Metals, kinda. Halogens, yes please. Metals, not really. Halogens, yeah, we really, really, really want an electron. So diagonal relationships on the periodic table, there's not that much to say about them. When you start in the beginning of the periodic table, lithium has properties kind of similar to magnesium, and beryllium's kind of similar to aluminum, one element diagonal down from them. As you progress through the periodic table, those trends pretty much go away immediately, so it's nothing too terribly exciting right away. So let's look at all these different groups of elements and some of their properties. We'll start at group 1. We'll go all the way across the periodic table. We'll try to be quick about it. These are NS1. That's their electron configuration. These guys will generally react with water to produce this kind of aqueous base and some free hydrogen gas. Sodium reacting with water is one example that students are generally excited about. A lot of them will react with free oxygen gas and they'll form oxides. And so here you have increasing reactivity going down the group. So sodium reacts with water more so than lithium would react with water. Here's what some of them look like. Mostly shiny metals. Lithium's pretty shiny metal. Sodium's a pretty shiny metal when you first cut it. Potassium, rubidium, cesium, they're all kind of shiny, metallic-y sort of things. Let's go to group 2. NS2, beryllium, magnesium, calcium, strontium, barium, those kinds of guys. Generally +2 ions, but you already knew that. Beryllium with water, not really a thing, but the rest of them will pretty much do a little bit of reaction with water. You might have to heat them or something to kind of get them going, but they'll do the same thing. Make a base, release some hydrogen gas, that kind of stuff. And here you've got gaseous water, and then here you've got a few of them will do it with liquid water even. They're so reactive because we talked about increasing reactivity going this direction that they'll even react with just regular old, cold liquid water and make the base and make hydrogen gas. So here's what they look like. Beryllium, magnesium, calcium, strontium, super shiny. Look at that thing. Barium, kind of weird looking thing. And then the sort of creepy green eerie glow of radium. So group 3, we're skipping transition metals because you guys know weirdness exists there. You go to boron, aluminum, gallium, indium, that kind of stuff. So here, aluminum plus oxygen, we can make aluminum oxides out of that. And aluminum with hydrogen gas, or hydrogen rather aqueous. So an acids release hydrogen in aqueous solutions. So aluminum plus an acid will make aluminum 3+ and release hydrogen gas. So here's what those look like. Boron. Aluminum you're pretty familiar with. They show like a little fence kind of thing made out of it, or a nail. Gallium, super creepy. Low melting point, so at room temperature it's a solid, but with the heat from your body, the hand, for example, here is melting it, so it's kind of cool. You can melt a metal in your hand, just ridiculous. And then indium. So group 4, carbon, silicon, germanium, what's SN? Tin, lead, that kind of stuff. There we go. So we got tin plus an acid gives us the tin cation and hydrogen gas. And lead will do the same thing, react with acid to give off hydrogen gas. And so here's some examples. Carbon, graphite, that's the form of carbon that's in mechanical pencil lead and your regular, wooden pencil lead too. Another form of carbon is a diamond. Then here's your silicon down here, germanium, tin, kind of a cool looking one. And then it looks like little lead pellets perhaps. So go to group 5, nitrogen, phosphorus, arsenic. And we see that they will react with liquid water, but not just regular nitrogen. We actually need oxides of these, which we can make. Nitrogen oxides and phosphorus oxides, we can make those, and those will react with water to make acids. So that's kind of cool. Here's a phosphorus and an oxide with water making acids. And maybe I shouldn't say that's that cool, because the nitrogen oxides, that actually causes acid rain. So let's pick a word other than cool. Interesting. It's kind of interesting. Here's some pictures of them. Liquid nitrogen, you can use that to keep things super, super, super cold. Phosphorus, both in white phosphorus, which looks a little more yellow to me, and then red phosphorus. Arsenic, what that looks like. Antimony, super shiny. And bismuth. Group 6, oxygen, sulfur. NS2NP4. So here we've got, again, the sulfur itself won't do it, but the oxides will. So sulfur oxide plus the liquid water will make an acid, H2SO4, which you're familiar with perhaps, sulfuric acid. And so here's sulfur, what it looks like, kind of this yellow crystal. Selenium, and then tellurium. That's what that one looks like. Let's get to group 7. We call these our halogens. The ions they form, we call them halides. And here they prefer to get one electron to become -1 charge. And these guys, fluorine is one example where they'd like to bond with hydrogen to get that extra electron. That's this example. And fluorine has such a high electron affinity, has such a high electronegativity, that if you add fluorine to a sample of water, it'll actually rip a hydrogen off of the already very stable water to make its own hydrofluoric acid. It's that greedy for electrons, and so it's kind of a cool reaction. And then we're increasing reactivity going this way. So iodine's not really as reactive or greedy as bromine, which really isn't active as greedy as chlorine, which really isn't as active or greedy as fluorine. Here's what they look like. Chlorine, kind of yellow gas, and bromine, kind of that orange-red color, and then iodine's this sort of purplish, brownish sort of color. So we get to group 8. These are our noble gases. They're completely filled subshells, highest ionization energy because they really don't want to lose any electrons. They don't have any tendency to accept extra electrons because they don't want any more electrons. They're super stable. And here's what some of the compounds of these look like. Xenon here is kind of red, and then xenon here is kind of yellow. And so we can make some compounds out of these. A number of xenon compounds exist, a whole bunch of them, and a few kryptons will that have been prepared. And so when you look at these groups 1A and groups 1B, they have similar electron configurations because they have one electron in their outermost orbital, and their chemical properties are quite a bit different though because of their ionization energies. If we look at oxides, our oxides made out of our metals are going to be pretty basic, and the oxides made of our nonmetals are going to be pretty acidic. So this is where we'll end here. Sir William Ramsay, he discovered 3 elements in 3 months. So holy smokes, right? Pretty decent chemist there. You can read about him on page 358 of your textbook, and it's actually a pretty cool story. 2 scientists, as opposed to competing with each other to discover these things first, they actually just worked together and like knocked out a ton of these noble gases and discovered the first noble gas, and it's a really cool story. So that is where we'll end with chapter 8.